All right, work, power, energy review. Number 1, the work done in accelerating an object along a frictionless horizontal surface is equal to the object's change in blank. Well, to answer this, you got to think about what work is equal to. Work is equal to a couple things. Work can be equal to force times distance. Work could be equal to a change in potential energy. And work could be equal to a change in kinetic energy. So I'm reading the problem, and it tells me that the work is done in accelerating an object. So it's telling me that it is speeding up, or it could be potentially slowing down. But this object is moving. So if I'm thinking about what form of energy is related to motion or velocity, that would lead me to believe that work was equal to the object's change in kinetic energy. The work equals a change in kinetic energy. If that object is accelerating, then it's equal to the kinetic energy that that object has along its pathway. Next question, let's see here. 2, 3, and 4 are all related to the diagram that you see up above. Okay, where I have a ball being released from point A. It's rolling down this ramp here. It's going up around the loop, and it's going to go up the other side. Okay, what I am asked to find out here in number 2 is how high would that ball actually go up the other side? Well, in this situation, I'm believing that energy is being conserved. The law of conservation of energy says that it's not going to change, it's going to stay the same. So if this ball starts at 15 meters high, then it's going to roll down here, it's going to conserve all the energy that it has, and it's going to reach the same exact point on the other side, which is also 15 meters high. Okay, because energy is conserved. So in other words, whatever height it started at, it's going to end at that height also. Number 3, describe the energy conversion. Okay, well, think about it. I got to think about it started at point A. What kind of energy did it have all of here at point A? It's at B. What kind of energy does it have all of at point B? It's going to go around the loop and then end up here. How much energy or what type of energy does it have the most of all the way here where it ends? Okay, well, I know that potential energy, gravitational potential energy, is dependent on height. At this point, at point A, the ball is at its maximum height. So the most energy that it's going to have here at point A is potential energy. Then as it rolls down the ramp, it decreases height and it speeds up until it reaches the bottom of its pathway. And it's moving the fastest here. It's got the least amount of height, so it has the most kinetic energy. Then once it leaves the bottom of the ramp, it's going to go around this loop. Not too concerned about that. Once it goes through the loop, it's going to increase height and gradually slow down. So it's increasing potential energy and gradually losing kinetic energy at this top. So the form of energy that it has the most of here is back to potential. Okay, number 4, what would the velocity of the ball be at point B, the bottom of the loop? Okay, so we started here at A. It's rolling down here at the bottom of the loop. We want to figure out how fast it's going here. Okay, so we already determined that it has kinetic energy down here at the bottom, and it's got potential energy up here at the top. And what we do know is that the potential energy at the top is equal to the kinetic energy at the bottom. Okay, so I'm going to start off by setting my potential energy equation up to my kinetic energy at the bottom. Now, I don't know the mass of the ball, but I do know that the mass of the ball is not going to change. So if I rewrite these two equations without the mass, you get GH equals 1/2 V squared. So if we start plugging in everything we know gravity is 9.8. We know our height was 15 equals 1/2 times velocity squared. So 9.8 times 15 gives me 147 equals half times velocity squared. To get this half to the other side, I divide by a half. And when I do that, 147 divided by a half gives me 294 equals v squared. And the last step is to take the square root of both sides. And when I do that, I get a square root of 294, which equals right here, 17.15 meters per second. Okay, number 5. Johnny weighs 4.5 times 10 to the second newtons. So what this tells me here is his weight. This is F or FW. He climbs a flight of stairs that are 15 meters tall. In 10 seconds, I want to know how much work he did. Well, this is telling me 15 meters tells me distance or height. 10 seconds tells me time. And I want to know what work is. Okay? So work is force times distance. Remember, work could be a lot of things. It could be a change in potential, a change in kinetic. What I'm given here is weight, which is force, and a distance. So I know F and I know D. I know work is equal to the force that acts over a certain displacement. So force times displacement equals, let's see, our force was 4.5 times 10 to the second times my distance, which is 15. And 4.5 times 10 to the second times 15 gives me 6,750 joules. Or you can also express it in scientific notation. It would be 6.8 times 10 to the third. Either one would be an acceptable answer. And the only reason I'm giving you an answer in scientific notation is because our weight was given to us in scientific notation. So you could see it either way. Number 6, how much work was done by an 80-watt light bulb that stays on for 3,600 seconds. So I'm trying to find work. I know power, and I know time. Well, I know that work equals, power equals work divided by time. And I'm trying to solve for work. Let's see, our power is 80, so if I plug everything in, I get 80 equals W divided by 3,600. Okay, now to solve for W, I can cross multiply, and I get 80 times 3,600 equals 288,000 joules. Number 7, a child applied a force to a boulder. There's the force, there's the time, but the boulder doesn't move. This is important because in order to figure out how much work is done, you need to know that there's a force and a displacement, and the force has to be parallel to the displacement. But if the boulder doesn't move, then there is no displacement. If there is no displacement, there is no work. Okay, so we have 0 joules of work because there is no displacement. There has to be some kind of movement in order for work to be done. If there's no movement, there's no work being done. Number 8, if the velocity of an object doubles, the kinetic energy of that object does what? Well, think of your kinetic energy equation. It says kinetic energy equals 1/2 mv squared. Here I'm comparing the velocity to the kinetic energy. So for the sake of this, I'm just going to remove the 1/2 and the m. I'm only looking at kinetic energy and velocity. If my velocity doubles, what happens to my kinetic energy? Well, if I put a 2 in here for v, 2 squared gives me a kinetic energy of 4. If I double my velocity from 2 to 4, 4 squared gives me 16. So when I double the velocity, because my velocity is being squared, it quadruples my kinetic energy. So Ke quadruples. It's 4 times greater, or it increases by 4 times. All right, number 9, draw separate graphs. Okay, so I want to draw graphs that are going to represent Ke, Pe, and Me. So I'm going to draw this is going to be my kinetic energy, this will be potential energy, and this will be total energy, or also written as Me. Okay, now if I toss the ball up into the air, at its lowest part of the pathway, it has the highest velocity. When it reaches the top, it's going to have the lowest or 0 velocity, so it's going to have the least kinetic energy. And as it comes back down, it's going to have the most kinetic energy again. So that graph is going to start off high, get low, and then high again. Since kinetic and potential are inversely related, this graph is going to be the mirror image of this graph right here. Okay? And it's going to mirror image because at the bottom of its path, it's at its lowest height, so it's going to have the least potential energy. When it reaches its highest point, it's at its greatest height, it has the most or max potential, and then it's going to come back down and decrease height again. So potential energy is going to start off low, get very high, and then very low again. Now, the reason, or because as a result of kinetic energy and potential energy being inversely related, that allows my total energy or my mechanical energy to remain constant. So constant line is, or constant graph is going to look like a straight line, and this straight line is going to be at the very top because my kinetic plus my potential equal mechanical energy. Okay, number 10. What time is needed to lift a 49 kilogram person a vertical distance of 5 meters with 500 watts of power? Okay, so I'm solving for, I need to know time. It gives me mass. I know vertical distance, so this could be height or distance. And then I know power. Okay, power is 500 watts. So my only power equation says that power equals work divided by time. Well, I have power, I'm solving for time, but I don't have work necessarily. But remember, work can be one of 3 things. It could be force times distance. I have distance, but I don't have force. It could be a change in kinetic energy, which includes velocity. But there's no velocity. I don't see any velocity up here. And work can also be a change in potential energy, which is a change in mass, gravity, and height. I've got mass, I know gravity, and I know height. So work is then equal to a change in potential energy, still over time. So what you end up with is power equals mass times gravity times height divided by time. So my power is 500, mass is 49, gravity is 9.8, height is 5, all divided by t. Okay? If I multiply 49 times 9.8 times 5, I get 2401. So let me scoot this over here. So I get 500 equals 2401, still divided by t. Okay, so I've got t as part of a fraction on the right. I want to make a fraction on the left and cross multiply. So 500 times t gives me 500t equals 2401. So in order to get t by itself, you have to divide both sides by 500. And when I do that, t comes out to 4.8 seconds. Number 11, what's the approximate difference in gravitational potential energy? So I'm looking for PE or GPE, between a 2 kilogram box sitting on a 1 meter shelf or the same box on a 3 meter high shelf. So the only thing that's different here is the height. There is a change in height going on. The mass is staying the same. The heights are different. I want to figure out what that difference is. So what I'm looking for is a change in gravitational potential energy, or simply just PE. So change in PE is mass times gravity times my heights. So that change is equal to the mass, this is the same, 2 times 9.8 times my change in height. It's going from, final height is 3, initial height was 1. When I subtract 1 from 3, I get 2 times 9.8 times 2 gives me a change of 39.2 joules. So the difference in gravitational potential energy between those two shelves is 39.2 joules. Number 12, how much power is done by an engine that does 2,000 joules of work? So this is W. In 45 seconds, that's time. I want to solve for P. Okay, so power equals work divided by time. I've got 2,000 joules of work, and it's being done in 45 seconds. 2,000 divided by 45 is 44.44 watts. Number 13 and 14, we're referring to this diagram down here below. It says, so what you're seeing here is you've got a ball at position A, and it's going to roll down the hill to B, and then up the hill to C, D, and stop at E. As the object moves from start across the surface, the sum of its gravitational potential energy and kinetic energy. So it's asking for the sum, which means the total. Okay, sum means total. And what is true about this, the total energy as it moves across? That it is, so total energy is constant. Okay, total energy stays conserved because of the law of conservation of energy. At what point is the kinetic energy less than at point C? So kinetic energy is dependent on velocity. If I am at point C, I need to figure out where my ball is moving the slowest, therefore where it has the least kinetic energy. Well, I know that at B, it has the most kinetic energy, it's moving the fastest. So anything higher than C, like point D, E, and A, are going to have less kinetic energy because they are moving the slowest. Okay, so it is actually A, D, and E. B is the fastest, has higher amounts of kinetic energy compared to C because it's moving the fastest here. Number 15, an athlete is working out in a weight room. According to the physicist's definition, the athlete does work on the weights when the force acting on the weights is what? To the motion. Okay? So the force acting on the weights has to be parallel to the displacement or the motion in order for work to be done. It has to be parallel. So if the athlete accelerates the weights from the floor to the shoulders, so you're getting a force that looks like this, you're getting displacement that looks like this going from the floor to the top. These two are parallel, just like we mentioned here, and they are in the same direction. They're both upwards. When the force and the displacement are both in the same direction, then my work that's being done is positive. Number 16. A car travels at a constant velocity up a hill from point X to Y. So here's X, here's Y. The car is traveling at a constant velocity. This is important. Explain what's happening in terms of potential energy and kinetic energy as it goes from X to Y. Okay? So you got to think about it. What is happening to the height? As it goes up this incline, my height is increasing. So because my height is increasing, my potential energy is also increasing. okay? Because as height goes up, potential energy goes up. Now, my velocity is constant. So if my velocity is constant, that tells me that my kinetic energy is also constant. Okay, because it's not increasing speed, it's not decreasing speed. So my potential energy is increasing, kinetic energy is constant while it's going up that hill. Number 17, if a ball were to have an initial velocity of 35 meters per second and then encounter a hill, what would be the height of the hill? So you're solving for h. So you have this ball here at A, it's rolling across here and it's going to gain height. We want to figure out what that height is. Okay, well, in order to do that, you need to understand that this ball has kinetic energy at the bottom. And the kinetic energy at the bottom is equal to the potential energy at the top. Now, I don't know that ball's mass, but the mass isn't going to change as it goes up that hill. So GH equals 1/2 v squared, where gravity is 9.8, h is what we're solving for, equals half times 35 squared. So if I complete or continue to solve this, 35 squared times 1/2 gives me 612.5 equals h times 9.8. So in order to get h by itself, it's being multiplied by 9.8. I need to divide by 9.8. So 612 divided by 9.8 gives me a height of 62.5 meters. Describe how the energy transforms as it travels along the ramp. Well, we just talked about it. It starts off with kinetic energy, and as it goes up the ramp, it gains potential energy. So the simple energy conversion is Ke to Pe. It's that easy. Number 19 was our warm-up. A custodian does work to push a trash can up a ramp. In order to push the trash can up the ramp in half the time, the janitor would have to produce how much power? So we want to figure out how much power he needs, or how much power he's going to produce when he pushes it in half the time. So our equation is power equals work divided by time. So an easy way to understand what's going on here is if you plug in some numbers to correspond to power, work, and time. So for example, if I have a work of 20 and a time of 2, that means that my power has to be 10. Okay? Now, if my trash can is being pushed in half the time, well, my time was in the denominator, it's 2. What happens if I decrease this time by half? So instead of 2, it's now, come on, 1. So I know that 20 divided by 1 does not equal 10. So when I decrease my time by half, look what happens to your power. It started off at 10 and now it's 20. So when my time is decreased by half, my power is doubled. My power becomes doubled. Number 20. The car with locked wheels skids to a stop while moving along a level highway. Describe how work is being done. Well, if the car tires are locked, the wheels are locked, that means the tires are rubbing up against that street. And when they rub, you create friction. So work is done when by the friction that's going on or created between the tires and the road. Okay. As a result of this work, the car gains, loses, or does not change its mechanical energy. Well, the friction is causing the car to slow down, so it's a decrease in velocity. So that is a decrease in kinetic energy, therefore it is losing energy. And if it's losing energy, that means the force and the displacement are in opposite directions. That is negative work. Situation can be best described as a transformation of what type of energy? Well, it was once moving, so it has to be either kinetic, or meaning A or C, or D, so it can't be B, can't be C, can't be E. Kinetic into potential, well, that would represent or imply that it's gaining height, and our situation says it's on a level highway, so it's not potential energy. Okay, when that car skids on the street, that energy is being lost by heat and sound. So when the friction is generated, it creates heat. The screeching of the tires is sound. That's also energy. Answer choice D. And the last one here, a tired squirrel with a mass of 1 does push-ups by applying a force to elevate its center of mass by 5 centimeters. So this is distance or height. In order to do a mere 0.5 joules of work, so this is W. If the tired squirrel does all his work in 2 seconds time, then determine its power. Okay, so I want to find power. And power is work divided by time. The work that's being done here is half a joule. And the time is 2 seconds. So 0.5 divided by 2 gives me 0.25 watts of power.